Hi everyone, this is going to be a video walkthrough of problem 3, asymptotic expressions on the exam prep worksheet for algorithmic analysis. So let's get started with part A. Part A reads, which of the following expressions are true? Check all that apply. Equations between asymptotic expressions, such as big O of f equals big O of g, means that all functions that are big O of f are also big O of g and vice versa. An expression such as big O of f subset big O of g means that all functions that are big O of f are also big O of g, but not necessarily vice versa. So looking at the first one here, what we'll notice is that this one is indeed true. The reason is that when we're looking at asymptotics, we can kind of ignore constants, right? This is a constant multiplier, right? It's a constant multiplier. And we also ignore lower order terms, right? So this is a lower order term. And the intuition here is that as n gets really, really big, which is how asymptotics is defined, this term dominates this n log n term because it gets bigger at a faster rate, right? So we can kind of see this left side kind of just reduces to big O or big theta of n cubed, which is the same as this right-hand side. So looking at this next one here, let's try to think to ourselves of what this means, maybe in simpler terms. So what this thing is saying is that for all k greater than or equal to 0, big O of n to the k is a subset of big O of n to the k plus 1. Okay, so kind of looking at that maybe in different terms, this thing is saying that every function f that's big O of n to the k is also big O of n to the k plus 1. So kind of thinking about this makes sense to me. The reason this makes sense to me is that if a function is big O of n to the k, it's never going to be slower than n to the k, right? If it's never going to be slower than n to the k, we know it's also not going to be slower than n to the k plus 1 because n to the k plus 1 is bigger than n to the k, right? So we can see that this one is true, right? Because intuitively, this is a looser bound, right? Okay, so looking at this next part here, kind of by symmetry, this answer is false, right? By switching big O with omega, we kind of assume the opposite happens. So if that didn't make sense, let's try to replace the thetas with omegas here. So we have a function f that's omega of n to the k. Is it also omega of n to the k plus 1? So we can kind of see here that that's not necessarily the case. Suppose that we define f to be theta of n to the k. All right, so let's say we have some function f that always takes theta of n to the k time. Right, always takes n to the k time. So we know that I can also say that f is omega of n to the k because it's not going to be faster or it's not going to be better than n to the k, right? Since it always takes n to the k time, this is a valid omega bound. Notice, on the other hand, that this is not a valid omega bound because it's just not true, right? This bound is saying that f is always going to be, or is never going to be faster than n to the k plus 1. Right? That's what this thing is saying. It's saying f is never faster than n to the k plus 1, which is false because f is faster than n to the k plus 1. F runs an n to the k. Okay, so we can kind of see here that by that reasoning, this one is going to be false. Okay, so yeah, moving on to the next part here. So this next part, I think it's kind of helpful to have like, not like a number line, but maybe an asymptotic equivalent of a number line. We have maybe constant runtime on the left-hand side, and maybe infinity on this right-hand side, right? This should kind of show like the spectrum of different runtimes. So if we have some function, let's say we have some function f that's omega of g, then what we can say maybe is that like, we have like f here, and let's say we have some function. Oh, okay. So if f is omega of g, that means g kind of upper bounds f, right? That means f is never going to be faster than g. So we know that f is going to be somewhere to the right of g. right? And then what we know here is that G is upper bounded by H, okay? So what I'm going to kind of like observe is that if G is upper bounded by H, I could say that H is here, right? I could also say that H is here, right? And since both of these options for H are equally valid and satisfy both of these two criteria, notice here that I can't say definitively that F is omega, that F is omega of H, right? So looking at both of these, right, if G is upper bounded by H, which is true in both of these pairs of G and H, right? And we say F is lower bounded by G, then notice that we can't really say anything about the relationship of F and H, right? Since both of these spots for H are valid. So this one is false. On the other hand here, if we just tweak this little thing right here, notice now that if H is upper bounded by G, that means that H has to occur at or to the left of G. So that means we know H might be somewhere here, right? So what we can kind of think here is that this one is going to be, shoot, I don't know why I X'd. Yeah, never mind, I'm correct. So what we can kind of think to ourselves here is that if H is upper bounded by G and F is lower bounded by G, F is also lower bounded by H, right? So intuitively, this is kind of why, if we think about it on this asymptotic number line I created, that we know F is going to be equal to or to the right of G, and H is going to be equal to or on to the left. H is going to be equal to or to the left of G, right? So we know that F is going to be equal to or to the right of H. Nice. Okay, so let's move on to the next part. So this next part is definitely like pretty challenging. I think it is a little like mathy, but it is in scope, and I think it kind of goes over some of the nuances between positive valued functions and how they play into asymptotics. So no worries if you guys didn't get this part. I think it's really challenging, but hopefully you guys enjoyed giving it a try. And if you didn't give it a try, pause the video, give it a try. It's a cool part. So yeah, let's get started. So suppose we have positive valued functions f0 to fk, where we define f of I of n to be equal to 1 plus f of n mod I, right? This is the remainder when n is divided by I, and we're going to pass in that same value of n. Okay, and this is for all I greater than or equal to 1. And our base case here, right, we can kind of think to ourselves, this is some sort of base case, is when f of 0 of n, that's just equal to 1. Okay, so we have like these functions f that are defined by this recurrence and this base case here, and we ask ourselves which of the following are true, and we want to check all that apply. And we're going to assume that n is greater than k. Okay, so the evaluation of f to the k of n, or fk of n, may run forever. So let's kind of think to ourselves about that one. So if I'm looking at fk of n, right, we know that this is going to be equal to 1 plus f to the n mod k of n. And one thing to notice here is that n is going to be greater than k, right? So if I'm looking at n mod k, this is going to spit out some number, right? It's the remainder when n is divided by k. And one thing really important here to notice is that this remainder is bounded between 0 and k minus 1. So we know the remainder is going to be at, like, the lowest it can be is 0, and the maximum it can be is k minus 1. And just to like kind of think about that to yourselves, maybe an example would help. Let's say n is equal to 5 and k is equal to 3. If you guys are thinking about 5 mod 3, right, notice that this is equal to 2. If we're thinking about 5, let's say we're looking at like 6 mod 3, right? If n is equal to 6, then this is equal to 0. If we're looking at 7 mod 3, this is equal to 1. If we're looking at 8 mod 3, it's again equal to 2. So kind of notice that when k is equal to 3, this remainder we have is bounded between 0 and k minus 1, right? So with this in mind, what we're going to notice is that f of k of n will recurse on, I'm going to say recurse here, right? Or recursively call some, let's call it f of I of n, where I is less than k, right? Because this remainder is bounded from 0 and k minus 1, so we know that this is going to be smaller than k. And kind of by that logic, if we keep applying this logic over and over, we're going to realize that eventually, if we're kind of looking at this chain of function calls, eventually we're going to recurse on f of 0 of n, which is our base case. So we can see here that this is a finite, right? So this is a finite number of calls. So this is not true that it may run forever, right? Okay, so the next thing here is that fk of n is lower bounded by log of k. So this one isn't true either. An easy way to see that for ourselves is if we're considering fk of n, where n is equal to 2 times k, what we're going to notice is that since this is how we define f subscript k of n, if n is equal to 2 to the k, then n mod k is going to be equal to 0 because k divides 2 times k, right? So what's going to happen is that this calls our base case. So we can kind of see that this value is 2, and we see that this value of 2 is going to be, what's the word for it? It's independent of k, right? So what we can see is that this is actually a constant. So we know that in the best case, the runtime of fk of n, the best case, is theta of 1, right? And it's constant time in the best case. So because of that, this is not an accurate bound because fk of n can be faster than log of k, right? So that's also false. And just kind of reiterating that example, we said, hey, in best case, fk of n is theta of 1. The reasoning is that when n, right, is equal to 2 times k, kind of this example right here, then what we're going to see is that that produces this kind of behavior where we're calling f0 of 2 times k, and we know that f0 is our base case. So we can see that we've done a total of like kind of 2 calls or 2 work, and it's constant. Okay, so the next thing we're going to notice here is that fk of n is big O of k. So this one is going to be true, and it kind of stems back to this argument here. If n mod k, the remainder, is bounded between 0 and k minus 1, the maximum that I can be here is k minus 1. Right? It's really important here to realize that this is the maximum value that we can recurse on. Okay, so notice that fk of n, the biggest f function it can call is f of k minus 1 of n, which so on, right, will, the biggest that this function can call is k minus 2, and so on. So kind of counting the number of terms in this sequence, there's a total of n terms, maybe n function calls, maximally. Right? So what I mean by that is that we're never going to have more than n calls just by leveraging this logic here, that k minus 1 is the maximum value that k can recurse on. Okay? So we can kind of see that indeed fk of n is upper bounded by k, right? Okay. So the next one here states that fk of n is equal to theta of 1 with respect to n. Okay? So this is also true. This one's kind of interesting here. So notice that as n, I'm going to write this one out. Let's get rid of some of this stuff here. Okay, so notice here. Yeah, that looks good. Notice, as n approaches infinity, the runtime of f of k of n doesn't necessarily increase, right? And the really important thing to notice here is that the runtime of fk of n is dictated by how big this number here is, right? So fk of n, right, is equal to 1 plus f of n mod k of n. So notice that this function's runtime, right, it's going to take longer, perhaps, if this value is bigger. So if this is big, the function might take longer, right? That's just maybe some intuition here, because we're kind of recursing on a higher value, so maybe we do more recursive calls overall, right? So notice that no matter what n is, no matter what this n is, no matter the value of n mod k is always, right? It's always going to be bounded, right, between 0 and k minus 1. So what we'll kind of convince ourselves of here is that even if n gets really, really big, the remainder, when we divide n by k, is always going to be between 0 and k minus 1, no matter what n is. Because of that, we can see to ourselves that this function is constant with respect to n. Okay, so the last part here, this one's pretty tricky, is that if we define n as k factorial minus 1, then fk of n runs in theta of k time. Okay, so I think this part is pretty cool. So let's go over it. Okay, so the first thing to notice here is that k factorial is divisible by 1, 2, 3, k minus 1, k, right? It's divisible by all the numbers between 1 and k. So k factorial, if you guys aren't familiar with factorial, it's equal to k times k minus 1 times k minus 2 times 1, right? Hopefully you guys might have seen factorial in 621A. So what we're going to notice here is that k factorial is divisible by 1, 2, 3, k minus 1, and k, right? All of these numbers, okay? So the next thing to notice here is that if I'm looking at k factorial minus 1, it is not divisible by 2, 3, k minus 1, k. I kind of notice here that if k, let's say k minus 1 divides k factorial, we know that k minus 1 isn't going to divide the number 1 smaller than k factorial, right? Because, let's just kind of think to ourselves as an example. Let's say that k is equal to 4. Okay, so if k is equal to 4, then k factorial is equal to 4 factorial, which is equal to 4 times 3 times 2 times 1, which is equal to 24. And notice here that if I'm taking the number 1 smaller, right, if I'm taking k factorial minus 1, which is equal to 23, if I'm looking at each of these factors here, notice that none of these factors, right, k is equal to 4, k is equal to 3, or k is equal to 2, none divide 23, right? None of these numbers divide 23, which makes sense because k equals 4, right? this divides 20 and 24, right? We can see k is equal to 3, divides 21 and 24. K is equal to 2, divides 22 and 24. Huh. So what we can kind of notice here, this is the really, really cool observation to make, is that when we're looking at 23 mod 4, this is going to be equal to 3, right? So what I'm doing here is I'm just kind of looking at this example, and I'm saying, hey, what's the remainder when k factorial minus 1 is divided by k, right? Just to give you guys some context, this is k factorial minus 1, and this is k. So what we're going to notice is that if 23 is divided by 4, the remainder is 3. If 23 is divided by 3, the remainder is 2. Right? If 23 is divided by 2, the remainder is 1. Right? So one thing we can kind of see is that if k factorial minus 1, right, the remainder, when that is divided by k, or let's just say for some I, right? For some I, where I is in the range, it's bigger than 1, but it's smaller than or equal to k, right? If we have some I, right, I in our example is like, let me just call these I, just to make it hopefully a little less confusing, right? If we're kind of looking at these possible values, and we're looking k factorial minus 1 mod I, where I is some number between 1 and k, right, not including 1, including k, then what we're going to see is that this is going to be equal to I minus 1. So this is the main thing to kind of notice here, right? And how we kind of came about that, we didn't really use any math. We just kind of went to an example. We generalized what we saw, right? Looking at this example, we said, hey, let's see what happens when we say k is equal to 4. If k is equal to 4, then k factorial minus 1 is equal to 23. So looking at 23 and looking at values of I, right? I is this new variable I kind of made to hopefully clear things up. So let's say I is 4, I is 3, I is 2, right? We're just considering values of I between 1 and k, right? Including k. Then what we can kind of see here is that when we divide 23 by 4, the remainder is 3. When you divide 23 by 3, the remainder is 2, and so on. So looking at this number and this number here, we see that's I and I minus 1 respectively, okay? So now what we can kind of convince ourselves of is if we're going back to this example, let me kind of get rid of some of this stuff here. Okay, so if I'm looking at f of k of n, notice that this is going to call 1 plus, well, n mod k is the same as k factorial minus 1 mod k, which we know is going to be equal to k minus 1 by that logic. So we know that f of k minus 1 of n is going to be equal to 1 plus f of k minus 1 mod k minus 1, right? Which we know that this expression is the same as k minus 2, right? This value is the same as this because of this rule right here, right? So what we can say is that this is f of k minus 2 and if we kind of continue this pattern, then eventually what we'll notice is that, let's kind of shrink this a little, move this to the side, that eventually we're going to hit f0 of n, right, which is equal to 1. And if we're looking at the total number of function calls here, the total number of calls is k. So the runtime of fk of n with respect to k is theta of k. So this function runs in theta of k. So this is indeed true. And yeah, that's all for problem 3. I hope you guys enjoyed this video walkthrough and have a good rest of your day.